Hi, I'm Dixon Sine. This is Data Structures in 5 Minutes, 3rd edition. Today I'm going to talk about trees, and trees are a very important data structure since it's one of the first that lets us really put items in a hierarchical structure, unlike linked lists. And so there are many applications for it, including natural language processing. So let's get started. A tree in mathematics is an undirected, connected acyclic graph. And a lot of these words are very intuitive, so I'll just give you examples instead of really defining them. A root is a node chosen exclusively without a parent. And so S is the root of this tree here. And a parent child, so for instance, a sentence is the parent of a noun phrase and a verb phrase. And the noun phrase and verb phrases are children of the parent. And an ancestor, so the verb phrase here has an ancestor, which is the overall sentence, and the verb phrase down here is the descendant of this overall sentence. And the noun phrase and verb phrase are obviously siblings, and because they can't really exist without each other. And a subtree, so a sentence is composed of a noun phrase and a verb phrase. This verb phrase, this entire thing, is a subtree of the sentence. And so the more complicated things regard height, depth, and height of the node. So the height of the tree is the maximum depth, and the depth is determined by the number of ancestors of a node, excluding the node itself. So if we exclude this adjective and just count 1, 2, 3, 4, we can conclude that the depth is 4, and since this is the deepest this tree will ever go, then the height of this tree is also 4. The height of a node, however, is something very different. It's 1 plus the maximum height of a child, or -1 if there's no children. So obviously the height here is 0, but if you keep going, you have 1, 2, 3, and a height of 4. So it's kind of inverted. Now let's talk briefly about how to represent trees. So I took this from lecture. A very good representation of a tree is a Sibtree, where you have a parent, an item that you store it in, the first child, and the next sibling. And so you have, for example, this tree here where the root is 3, then you have 2, 4, and 6. 2, 4, 6 are siblings. Then you have 10 and 12 who are siblings. 14 is the first child of 4, and 16 is the first child of 6. These 4 are not siblings, and you can see them here in the actual tree representation. And so this is how the Subtree representation works. Next, I'll talk briefly about tree traversals. There are 4 of them. The first one is pre-order traversal, where you visit each node before the children. So we visit the square, then the triangle, circle, X. Then we go back to the second child. Here, diamond, heart, and club. Post-order is a bit different since you visit the children first before the node itself. So we have here this heart, club, diamond, and then square. You can see that the children are first, then the node. Children are first, then the node. Children are first, then the node. And for level order, you go level by level. So it's very intuitive here. And you can figure this out on your own. And in order is a traversal only for binary trees. And it's only for binary trees because you go left, middle, right. And so you have left, middle, right, and here's the middle, and you have left, middle, right. Alright, that takes care of the 4 traversals of a tree that we'll go over. And finally, we're going to talk about binary trees. And binary trees are special in that no node has more than 2 children. So I saw with the Sibtree representation that there could be more than 2 children, but for binary trees, such as this geometric tree right here, can only have at most 2 children. And the main thing to note about binary trees is that they are not necessarily balanced nor sorted. So they're binary search trees and they are balanced search trees, but in general, binary trees are neither balanced nor sorted. And every child is either a left child or a right child. As you can see in this representation, it's very logical. There's a parent, an element, a left child, and a right child for each node. Finally, the properties, I'll go over them really quickly. The first one is leaves. There's at least one leaf, of course. There are at most 2 to the h leaves. So if you draw a quick one here, you can see that there are 2 to the 2 at most at the bottom for a complete binary tree. For internal nodes, you can either have the height of the tree at the very least, or you can have 2 to the height minus 1 for the maximum. And for the height of the tree, it's either log base 2 of n plus 1 minus 1, or n minus 1. And this is the min, this is the max. So for a complete tree, there are 2 to the height at the very least, right? Because for a complete tree, this is minimized. This will give you about n over 2 leaves. And this showed up on our midterm, and something good to know. And so this is pretty much it for trees.